Hello. In the last video, we have been discussing about the hybridization. We have understood Sp, Sp2 and Sp3. Okay, Sp is when the number of regions of electron density is 2. Sp2 is when there are 3 and Sp3 is when there are 4. And we have also understood the shape of Sp is going to be linear, shape of Sp2 is going to be planar, and shape of Sp3 is going to be tetrahedral. Okay, so that's what we have understood. Let's now, before we start the hybridization which involves the d orbital, let us do some quick questions so that with whatever we have studied so far, so that this concept becomes super clear. Okay, so if they might give you a question like, in carbon dioxide you have to identify the type of hybridization of every atom. Okay, so first what you need to do is write its structure. Okay, so this is the structure of carbon dioxide. Carbon has got four valence electron and all the four are bonded. Correct. Now let us start with carbon. How many regions of density? 1 and 2. Correct. So 2 regions. If there are 2 regions, what is the kind? It is going to be sp hybridized. Now for oxygen, you have to write the lone pair also. 1, 2, 3, 4, 5, 6, 7, 8. So it is like this. 6 electrons and this is how it is shaped, right? So this is how we'll be writing. So for oxygen, for both oxygens, they are having the same arrangement. So you have 1 region, 2 region and 1. Pi is not considered, right? So 3 regions. So this is sp2 hybridized. Okay. That's it. You just have to write this. And what will be the shape? Since the central molecule is sp hybridized, it is going to be a linear shape. Only around the central, if there are lone pair of electrons, that is when it will take that bent shape. Okay, please remember this. Now, if you little bit want to understand what is actually happening here, let us write it for carbon. Only for this, it's not required. You only have to write this. Carbon, what will be the configuration? 1, okay, 2, 3 and 4 in the excited state. And if it is sp hybridized, these two will mix and these two will be in unhybridized state. Correct. And that there are 2 pi bonds here. That means I need 2 unhybridized, which is correct, right? So if you want, how do we draw this? Carbon dioxide. Okay, so this is your carbon. These are the 2 sp hybridized orbitals. Okay, so they form one bond with oxygen. Now for oxygen, how do you write which? How do you know which one is? It is sp2 hybridized, right? So let us write it for oxygen also. So 1s2, 2s2. It is like this. Correct. This is the case in for oxygen. So the p orbital kind of overlaps, right? So here I'll just write it. This is for oxygen, and here also you have 1 oxygen. Okay, and the this unhybridized d orbital of carbon, one is x and one is y. Okay, they will overlap with the unhybridized orbitals of this. Okay, so that's how it results in the formation of a pi bond. Okay, carbon will have 2 because it has to form. So px of this will overlap. So px will overlap, and here it will be the py which will be overlapping. Okay, overlapping is always with the same px, px, py, py. This is px. This is px of oxygen. This is py, py of this oxygen. That's how the overlapping will happen. All right. Yes. Okay. Yes. All right. Now here I did not explain this. Let me also explain this. This is sp2 and this is the unhybridized orbital, right? So that's how you have it here. Okay, the only thing is here it will be in the one of, there are 2 oxygen atoms, in one it will be px and one it will be py. That's when the carbon is able to make the respective pi bonds, and these are, they are already containing a electron pair, right? So they will not participate in bonding. And if you, okay, maybe let me just draw it again so that it's clear to you. You don't need this, you only need this, but I'm still just telling you. So carbon is sp2 hybridized, right? So this is sp2 carbon. Okay, so one is This is your P's X and this is your Py, okay, of the carbon. Alright, now oxygen will have 3 sp2 hybridized orbitals, right, and 1 unhybridized, sp2 it is, correct. So out of the 3, 1 will form a bond with oxygen, correct. So it will be like this hybridized, this is oxygen, okay. Here also it will form a bond like this. This is your oxygen. Wherever there are regions of overlapping, you will have to say there are electrons, okay. So this is the sharing of electrons. Alright, and there are 2 lone pairs. These are your lone pairs, right, which are not bonded. Write it here. Alright, so now sp2 will have a a trigonal shape, right. So it will be like this and it will be like this. So this will have lone pair, this will have lone pair, correct. And the same is the case with here. It will be having lone pair, it will be having lone pair, okay. And because of that lone pair, though this is it will bend like this, and that's why the shape overall is going to be linear. And so this is taken care, this is taken care. This will not be actually visible as a plane, it will be condensed, right, because you remember, if it is lone pair, the orbital it gets condensed. That's the reason it gives you that linear shape, right. So the lone pair is actually here, okay. So you will feel it to be like this, 2 lone pairs here, and the unhybridized, which will pair with this pi bond, okay. So that's how it is. It's a little messy, I know, but you don't have to understand that. Just so that the topic is clear, I'm just writing all the diagrams. Alright, so let's do one more. In the case of nitrogen, okay, so nitrogen has 5 electrons, 3 of them are bonded, so 2 will be lone pairs. This is the structure for nitrogen. What is the type of hybridization? 1 and 1. There is only, you know that it is linear, that way also you can think, okay, but in terms of identifying the region of density, 2 and 1, 2 and 1, right, sp and sp, done, correct, and that's why it is linear, okay. Next, ozone. Let us try understand why ozone is bent. Okay, so let us first write ozone. You know it is like this and it is like this. Okay, so this oxygen, there are 2 lone pairs. Okay, in this there are 3 lone pairs. This is actually a coordinate bond. So this has got a minus charge, this has got a plus charge. Both the electrons are here. So 1, 2, 3, 4, 5, 6, 7, 8. Right, so this is how it is. So the oxygen had, this oxygen had 6, 1, 2, 3, 4, and it has shared this, and 5, 6, both it has given. So this is actually a coordinate bond. But anyways, okay, now if you look into the hybridization of each oxygen, let us talk about that. This oxygen, 1 region, 2 region, 3 region and 4. Okay, so 4 means it is sp3 hybridized, correct. Let us talk about this oxygen, 1 region, 2 region, 3 region. You cannot consider this. This is a pi bond. So 3 region, so it is sp2 hybridized. And for this oxygen, 1, 2, 3 and no, this is actually 1, 2 and 3. Yes, 3 again. So it is sp2 hybridized. Now sp2 should actually give you a planar, correct. It should give you something like this. But since this electron is not contributing, it's just an lone pair, it is not a bonded pair. Lone pair is close to the nucleus, right? See, imagine this is, it should be like this, alright? The typical sp2 structure will be like this, where here you have that central oxygen, and here you have 1 oxygen, here you have 1 more oxygen, these 2, and here, what is it? It's lone pair. When there is lone pair, what is the point in bonding? This is not there, there is no atom here, right? So won't it be bent? That's exactly why this is bent. Okay, so these were some of the questions. If you want to identify the type of hybridization, you just have to find the regions of electron density. Alright, so now before we get into the we have to study 2 types of hybridization which involves d orbitals in detail, but I will give you the list of all of that for now. Let us first write the list. We will start from the beginning. This is a region of density. How much? It is 2, right? S1s and 1p, okay. And I told you percentage of p is it is less here, so it is a short bond comparatively. Okay, next we will write sp2, it is slightly long, and sp3, it is having the longest, right?
So 3 regions and 4 regions. The shape is linear or 180 degree. This is going to be a planar, triangular planar. Okay, so 120, and this is going to be tetrahedral. Okay, now if there are lone pairs, it will just distort. Okay, let's not worry about all that cases. We'll only remember this. Okay, this is the angle. Example, methane. Sorry, this I have put in this way, right? So this is triple bond. Only when carbon is involved, I'm just telling you this. There are so many other examples which I have already done, right? For this, it is BeCl2 or carbon dioxide, which we just now did. For this, it will be BF3, and for this, it will be methane. Okay, or anything. There are many others, but let's not worry about it. Now there is one which is DSP2. Okay, so the one d orbital, one s orbital, and two p orbitals, they mix to give you a DSP2. The regions 1, 2, 3, 4. So this is also having 4 regions, but the shape of this is going to be a square planar. Now why it is a square planar? Because ultimately when you have 4 hybrid orbitals, the best arrangement is in the form of a tetrahedron. Okay, but for many reasons, because once a d orbital is involved, it is leading to a slightly complex, it is becoming a little more complicated because there are 5 d orbitals. It depends on which d orbital is getting hybridized and all that. So we have to get into a little details which is not in the scope right now. Okay, so for now, for a particular geometrical reason, it is square planar. And if it was tetrahedral, then the repulsion would have been a little greater. That's the reason it is acquiring this. I know this is like contradicting, but there are other reasons which makes it quite a square planar. Okay, and if it is square planar, it is going to be 90 degree. The examples for this are all the complexes. Alright, so you have a quite, I just check. Yes, this you will be studying in your coming, that is 12th standard in coordination compounds. Okay, CN4 2 minus. Okay, so these are all coordination compounds. Okay, and even with the platinum. Okay, PtCl4 2 minus. Okay, so these are all complex ions. For now, you just note this. You don't have to remember this also. Because we are in the flow, we are telling. Okay, the next, this is 4 regions. Now let us talk about 5 regions. Okay, that is Sp3d. This is something that you will be studying in detail. Sp3d, 1s orbital, 3p orbitals. See, now if I write d here, it means it is the d orbital of the penultimate shell, the previous shell. If the outermost shell of is 4, then this here will be the 3d. And if I write it like this, it is 4s, 4p and 4d. Okay, so this is for the penultimate shell, this is for the ultimate shell. Okay, so this region is 5, and if it is 5, you already know it is going to be trigonal bipyramid. Okay, bipyramidal. Okay, it's something like this, right? Trigonal, central atom, 3 atoms, one on top, one on bottom. The angle here is going to be 120 and here it is 90. Alright, now typically all the hybrid orbital should have the same energy, but here you see they have a different bond angle. That is also something which we will not study now. Okay, because you know this is actually not, this is the hybrid orbital. This kind of hybridization is happening in 2 steps rather, sp2 and pd it is. Okay, which we will not it is beyond the scope. For now, let us understand this in detail. So the example for this is PCl5. Alright, so yes, this is Sp3d which we will be doing, and then you will have Sp3d2 or D2Sp3. Okay, both are different, but both of them have got 6 regions. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and the shape is going to be octahedral. You know this already. If there are 6 regions of electron density, it is octahedral. Okay, so square here. Okay, like this. Okay, and one here, one here. SF6 is the example. Alright, so this is what you will be knowing. Now other than that, these are all when you don't have lone pairs, right? Everything is bonded. If you have lone pairs, you've already covered that geometry. It is just that, but it is anyway beyond scope. Okay, so This 3 which we have done in detail you should be knowing, and these 2 which we will be discussing now. Alright. Yes, I think you have one more. Sp3d square is 1 minute. Sp3d square, Sp3d, it should be Sp3d. I have covered, right? Trigonal bipyramidal. Yeah, 5 will have one more, but that's lone pair. Anyways, let's not worry about it. Okay. So ultimately in D, you remember this table for the this thing. The difference between these two I forgot to tell you. This is again the mixing of S, 3p orbitals and 2d orbitals of the next shell. Anyways, we are going this in detail. And this is 2d orbitals of the previous shell and S and P of the ultimate shell. Okay, so remember this. This is the summary of this. And this, all this from here, it's going to be very important for the next year's coordination compounds chapter. Alright, now having understood that, let us understand Sp3d and Sp3d2. Okay, so that will complete the hybridization. Yes, let us now understand the detailed structure about Sp3d hybridization. Okay, so what is this? 1s plus 3p and 1d. Okay, 1d of this ultimate shell. They mix to give you how many? 6. Okay, sorry, 5. So 3 plus 1, 4 and 5. 5 Sp3d hybrid orbitals. Alright, now how are these orbitals directed? They are directed, 3 of them are like this, okay, like this and like this, like a equatorial plane. 3 of them are directed along the equatorial plane, and 2 of them will be like this. Now I don't know how to show this, it's a little tricky to show this. Okay, let me still try. Okay, for first I will just tell you like this. So this is 1, okay, 2 and 3. Okay, so if we join, you will have an equatorial plane, and the remaining 2 are actually perpendicular like this. Okay, if I had another plane, it is not like overlapping. The 3 are in this plane, one is on top, one is on like top and bottom. That's how it is. Alright, so this is axial, so this is equatorial, right? So the 2 orbitals are what we call as axial orbitals, and these are what we call as equatorial orbitals, right? So these are called as equatorial orbitals because they are in the equatorial plane and they are along the axis, so they are called as axial orbitals. Alright, so in the equatorial orbitals, you know the angle is 120 and here the angle is 90. This is something that you already know. Okay, and the example here is PCl5. Let us understand what it is. Which is the central atom? Phosphorus. Phosphorus atomic number is 15. 1s2, 2s2, 2p6, 3s2, 3p3. This is the configuration. Correct? So we will only write for this. In the ground state, it is going to be like this. Phosphorus and nitrogen in the same family. In the excited state, what will happen? Look at that. In the excited state, where it can go? Okay, it will actually go to the D. You have D orbital which is empty. Phosphorus is in the third period, right? It has a D orbital which is empty. So in the excited state, this will come here. Correct? So now, okay, look at that. Now isn't it D S wait. S, this is S, P3 and D. Correct? So this is Sp and 3. You can write it like this. 1, 2, 3, 4, 5. You're totally having 5. So 1 electron each. So each one is Sp3d. This is also Sp3d. Each one in diagram wise. And orbital diagram wise I have shown you. Correct? Now there are 5 chlorine atoms. Chlorine has p orbital, which is the 2 chlorine, right? So 3p orbital, one of them is empty. So that will come. So let us write it here again. If I just have to show overlapping. Okay, so first I will draw this. It becomes easier for me. Okay, so I think I can just twist it. It becomes easier for me to show. Right? So let me write it like this. 1, 2, and 3. Okay, so this is forming an equatorial plane. So these are your, this is one sp3d, second and third, each one is having one electron. So it will hybridize with the chlorine's p orbital, right? So it will be like this. This is 2 chlorine, chlorine 1, chlorine 2, and this is chlorine 3. Okay, and you have one along this also, right? So it is like this. So here you will have another chlorine. Okay, and here also you have one. So this is your, these two are your sp3d of phosphorus only, right? And you have one more chlorine here. Okay, so here you will have 2 electrons, right? So axial bond is going to be 90-degree bond angle, equatorial bond angle is 120-degree, and always remember axial bond length is longer because it is making 180 degrees, right? Whereas equatorial bond length is going to be shorter. Okay, so all these three are identical, these two are identical, but they themselves are not identical. Now why usually when hybridization is there, they should have the same symmetrical, same energy, but for reasons which you will study later, you will understand why it is so. Okay, so this is about sp3d. Now that you have understood this, we will now move to the last kind of hybridization which you should know, and that is going to be sp3d2. sp3d2. Alright, now sp3d2 is when there are 6 regions, right? So one s orbital mixes, I told you the shape there, yes, 3p orbitals plus 2d orbitals of the uh, ultimate shell, because it's written after, and you will get 6 sp3d2 hybrid orbitals. And when there are 6 orbitals, what is the best geometry that you can have? Okay, so you can, this will be a square planar at the center. This is a central atom. 1, 2, 3, 4. Okay, 4 here and 2 which is perpendicular. Imagine this to be a square, 2 perpendicular. All the 4 vertices of a square, you will have it. Here is the central atom. Generally we say that equatorial and all that, but here it doesn't matter, right? All the bond angles are equal here. This is 90, this is 90. Inside the square everything is 90. Here also it is 90. There is no concept of equatorial plane and axial here. Please remember that. Okay, so let us now take an example. That's all I have to tell here. So the example is sulfur fluoride, correct? So sulfur atomic number is 16. Let us write it: 1s2, 2s2, 2p6, 3s2, 3p4. Next, it just comes after phosphorus, right? So what will be the configuration here? This will be 4, right? 1, 2, 3, 4, and this will be empty. Okay, so in the excited state, one electron will jump here. This will also jump here because it has to accommodate 6 fluorine atoms, right? So this will be singly occupied now. This will also be singly occupied, and here these two will have this. Correct? So now these 6, 1, 1s, 3p and 2d of the same shell, that is the ultimate shell, they will hybridize to give you 6 sp3d2 hybrid orbitals like this. You will get 6 of these kinds. And how are they arranged? They are arranged in this. 4 of them will form a plane, square plane. 5th and 6th will be arranged like this. Correct? And when what is that fluorine? Again, p orbital, 1 will be here, 1 will be here, 1 will be here, 1 will be here, 1 and 1. Okay, that's how the hybridization takes place. I hope it's all clear. Sp, 2 regions, shape is linear. Sp2, 3 regions of density, shape is going to be planar. Sp is when you have triple bond, because it's obvious, right? Only 2 bonds are there, so you need that. Sp3 is when S and P, 3p, tetrahedral. DSP2 is square planar, though there are 4 regions. And Sp3d is going to be trigonal bipyramidal, 5 regions. Sp3d2 is going to be octahedral. Okay, even D
D square means it's the previous shells, but I think we don't have to discuss that. Alright, so this much is enough if you know. Alright, so that's about hybridization. I think we can go ahead and start with molecular orbital theory. Maybe the intro part I will do, the writing, how do we write the molecular orbital diagram, we will take it up in the last video, next video, which will be the last video. Alright, so now first of all, what were the limitations of your VBT? Okay, there were so many limitations. We never studied about para and dia. I think you will be studying about magnetic property here. Okay, but actually even in VBT we can tell para and dia. But let us not iterate there, because we had only understood VBT in terms of atomic overlapping. That is, in order to explain the shapes, it introduced the concept of overlapping of orbitals to form a bond. Correct? That is what was very, very beautiful. And also it also explained, was successful in explaining the geometry. And later it figured out that it is not just pure orbitals which overlap, but also hybridization can happen. But there are a lot of limitations. Okay, like for example, in some of the cases, odd electron configuration they were not able to explain. Okay, and even in the case of oxygen is actually paramagnetic. If you analyze that from the point of view of VBT, you get it to be diamagnetic. Okay, so what is diamagnetic, paramagnetic, all that we will come. But I think the atomic VBT was only talking about valence bond theory, right? That means it was talking about the orbitals which are there in the valence shell of the atom. But when molecules are formed, there are two atoms coming together. So what is the point if I only learn about this orbital and this orbital? There is something, and there is overlapping of orbital, and that forms something else. Okay, so that was not covered in VBT. It was only explaining everything from the atom perspective. Atoms electronic configuration, atoms orbitals, atoms hybridization. It never spoke about what happens exactly when a molecule is formed. I mean, though it explained that, overlapping is happening, hybridization, then overlapping and all of that. But when you considered overlapping, we were only considering the overlapping between two atoms. But after they overlap, what happens is what is explained in the molecular orbital theory. Okay, so Hund and Mulliken, they were the one who actually put forward the molecular orbital theory in order to explain the relative bond strength and magnetic properties. So bond strength also they were not able to explain in the VBT better. So this theory attempted to explain the bond strength and magnetic properties. Alright, magnetic properties. Now we will just understand the main features of this theory. Alright, so there are a lot of diagrams which will actually explain you, but for now I will tell you it is in the simplest way. Alright, so imagine this is hydrogen, right? And a hydrogen is having a single electron. So this is the nucleus, it has got one electron. This is also hydrogen, which is there a little far away. This is the nucleus. Okay, now when they are coming together, remember in VBT we studied this, as they come together the attractive forces begin to develop, it increases, and a point comes when the attraction and force of repulsion are just equal, and that's when that is the optimal stage for the two atoms to overlap. The maximum possible overlapping will happen, and that results in the bond formation, which leads to stability of the molecule where energy is released. That is called as bond enthalpy. Correct? Now, what happens when it is actually happening? So this is s orbital. Think in terms of orbital. In reality, 1s orbital and 1s orbital are coming closer, and it's the overlapping of ss orbital. There is no hybridization in H, right? So the two ss orbitals, they overlap. And once they overlap and form a molecule, this ceases to exist. Alright, they are now a part of the molecule. Imagine two people, I shouldn't be explaining it this way, but I feel this makes
it easier for you to understand this concept. Imagine two people getting married, like they were very far, okay? The hero and the heroine, they started coming together and they got married, all right? So once they got married, it is like, you know, your previous identity is lost. Now you are becoming a Mr. and Mrs. and all that. It is not that, you know, they are the same thing as before, right? Some changes would have happened. And that is what exactly we are going to study in molecular orbital theory. So once they overlap, the atomic orbitals cease to exist. We will now, they mix and they give you something called as molecular orbital. Or let us say if you're adding, what do I say, coffee, sugar and milk and everything, is the identity of milk there as such? I mean, you can feel that milk is added. You can get the coffee taste. You cannot eat the coffee powder as such. But together they form coffee, which has got individual properties, but it is a different thing altogether, right? And that's exactly what is happening when a molecule is formed. All right, so let us now understand the important points which are covered under this theory. First, let us understand the points and then I will be explaining you what exactly these points talk about. Okay, so first of all, atomic orbitals, okay, atomic orbitals, henceforth I will be abbreviating like this, molecular orbitals, MO, okay, of comparable energies and proper orientation, very very important, comparable energies and proper orientation only can overlap to give you molecular orbitals. That means if comparable energies, if you have 1s of one atom, it can overlap with 1s of another atom, okay, two atoms, and it will be giving you one, now two it will be giving you, but it will give you molecular orbital. Let us understand that, okay? And this is about comparable energy. 1s can only overlap with 1s to give you this. Orientation also. If you are talking about P and if you are saying it is P, PZ and PZ of two atoms, only PZ and PZ, because PX, PY and PZ are degenerate, so their energies are fine. But orientation also matters, which means PX and PY will, even if they overlap, it is not leading to the bond formation. We have already studied this. PX is like this, PY is like this. How will they overlap? You know, there is no, they are in a, you know, the plane is not allowing, like, you know, it is like this. How will they overlap? Oh, right. So overlapping is fine, but it will not, the electron density is not getting overlapped, right? So that is what is the meaning of this. So atomic orbitals of comparable energies, that means 1s with 1s of second atom, 2p z and 2pz, 3s and 3s, okay, 3py and 3py, something like that, okay? This is the first point. Now, the number of molecular orbitals formed, okay, is equal to the number of atomic orbitals, okay, atomic orbitals overlapping. Okay, now we are only going to study diatomic molecules, okay, and that too which are homo, means same type, okay, homoatomic, or I should not say same type of atoms. Because this molecular orbital theory is actually very very complex, it's very very vast, all right? So we are only just starting this, and when you're starting something, you will not be learning everything in detail. We are slowly building on concepts step by step, okay? Eventually when you specialize in this field, you will realize how complex it is. You're not even studying 1% now, all right? So anyways, yes, so the total number of molecular orbitals formed is equal to number of and in my case I told you it's only two. So if there are two atoms which are coming together, then how many molecular orbitals will be formed? Two. Okay, so visualize them as like, you know, arrows. If you have seen Mahabharata and all that, there are arrows, the one from the Krishna side and one from the Duryodhana side, whatever it is. And what happens, imagine they both meet and they results in two things. Okay, so if there are two atomic orbitals overlapping, you will get two molecular orbitals. If there are three, you will get three. Okay, if there are four, you will get four, but we are only studying diatomic. That means when two atomic orbitals overlap, two atomic orbitals of two different atoms, they come together, they give rise to two molecular orbits. Okay. Now the overlapping of atomic orbitals forms two types of molecular orbitals. Alright, one is called as bonding molecular orbital and another is what we call as anti-bonding molecular orbital. Bonding molecular orbital is considered to be it is the energy it is that orbital which is having lower energy, and this is something which is having higher energy. Okay, and this is represented by a star. Now, what is the meaning of this? Let us say the two atomic orbitals, 1s, 2s, whatever, they will have certain energies, right? When they overlap, the energy is redistributed. It forms one atomic orbital which is having lesser energy. This is your bonding orbital. It will form one more which is having a greater energy, and that is anti-bonding molecular orbital. Okay. Now this is having lower energy and hence this is stable. So if any electrons are there here, then it leads to stability. Whereas this I can say this causes attraction of the atoms, and this is the one which is responsible for the repulsion. Alright, that is what it is. You can also visualize this in terms of maybe the next part I will be telling you that. For now, let us not overcomplicate it. Okay, now it's very simple. Two atoms are coming closer. When they overlap, okay, it results in two molecular orbitals. One with the lower energy than the atomic orbital, that is bond orbital, and anti-bonding molecular orbital. Now, molecular orbitals are the next point here. Molecular orbitals are polycentric. Okay, whereas atomic orbitals are monocentric. See, atom will have one nucleus. Now, there are two atoms coming together and forming a molecule. A molecule now will have two nuclei, right? So, that's why it is polycentric. Electrons are filled into various, the electronic configuration is following all your Hund's rule, Pauli's rule and everything. Okay, Aufbau's and everything. Whatever rules we have studied for filling up electrons in the atomic orbital, the same rules are valid here also. It is just that instead of two atoms, now we call them as two molecular orbits. That's all. Alright, so yes, these are the things. What will be the difference between an atomic and the molecular orbitals? Atomic is monocentric, this is polycentric. Atomic orbitals are less stable. This is leading to stability. You see that lower the energy, molecular orbital is more stable because of the lesser energy, right? And atomic we generally say SPDF. Here we call it as bonding, anti-bonding, sigma, pi, and the names you will understand eventually as we proceed with the chapter. Okay, so I hope this is very clear. So then when the two atoms come together, they form molecular orbitals. There are number of atomic orbitals overlapping will be equal to the number of molecular orbitals which are formed. Okay, lower energy is bond, higher energy is anti-bonding. Yes. Alright, maybe yeah, I can take a little bit of the theory behind there's also something called as linear combination. I'll probably talk about that another 5-10 minutes, and we should be good to start with the final thing in the last video. Okay, so there is something called as linear combination of atomic orbitals. Okay, so we are going to learn that now. Okay, now according to wave mechanics, in the second chapter, that is atomic structure, we understood that electron is having dual nature. It can sometimes act like a particle and sometimes like a wave, correct? And any wave is graphically represented like this, and it will have wave function and wave characteristics. right? Now this wave function, if you remember, was given by the Schrodinger's wave equation, and that is nothing but your psi. And remember this wave function, if you solve this equation, you will get the probability of finding an electron in a atom, right, or in an orbital to be precise. And it also gave you the 4 quantum numbers, the solution of this, which tells you the exact location of each electron in an atom, right? Exact address in the sense where they lie basically. I cannot get the exact address because I can only find the probability of finding an electron. Right? Now, molecular orbitals are formed by linear combination of atomic orbitals, and this is happening in 2 ways. There are 2 ways in which molecular orbitals are formed by linear combination. Linear is along a line because we are talking about 2 here. The 2 atomic orbitals will overlap along a line, correct? So let us now understand that. Okay, now molecular orbitals are formed in 2 ways. What is the meaning of 2 ways? Now imagine, since I am saying electron has a wave particle, how can 2 waves interact? Now replace electron or replace orbital, okay, replace them by a wave. So instead of saying 2 orbitals are overlapping, how 2 waves overlap? There are 2 ways. If the crust and crust fall on each other, okay, let me draw like this for now. Okay, here only. So if the crust and crust fall on each other, their amplitude shoots up. It will be like this. This is what we call as constructive interference. We have done this in, you will be studying this in waves, but little bit I explained in atomic structure as well. And if there is one wave and the second wave trough is like this, then it results in a diminished wave. Correct? The amplitude shoots up, the amplitude becomes lesser here. It will be the difference between this. Okay, and that is what we call as a destructive interference. Okay, if constructive interference happens, that results in the formation of molecular orbital, and if destructive interference of 2 electron waves happen, that results in the formation of anti-bonding. This is bonding molecular orbital, okay, and this is anti-bonding molecular orbital. Okay, so if I have 2 atoms, let me say this one wave is of atom A and this is for atom B, 2 atoms. Okay, now how will you write this molecular orbital? You can write it like this, psi A plus psi B, and this is your constructive interference. And if you write it as psi A minus psi B, that will be your destructive interference. Alright, so if the 2 waves are in such a way that the amplitude shoots up or it is constructive, it results in the bonding molecular orbitals. Alright, and the destructive, it results in the formation of the anti-bonding molecular orbitals. Addition of atomic orbitals, that is what we call as constructive interference, correct? Subtraction is what we call as destructive. Addition will increase the attractive force, right? Now this, imagine the amplitude is shooting up. What is the meaning of that? Remember we had resonance, okay, you will be studying next year, sorry about that, yes. But anyways, there are 2 amplitudes which are adding up, it is helping, right? So that means the force of attraction is increasing. So this leads to the increase in the force of attraction between the atoms. This leads in the decrease in the force of attraction, or there is repulsive forces which are developing. Alright, so let us just summarize. Bonding atomic orbital and anti-bonding atomic, bonding molecular orbital, okay, and anti-bonding molecular orbital. Okay, this is basically formed by the addition of wave functions. Okay, this is formed by the addition of wave functions, or when I say addition, crust and crust following on top of each other. This is formed by the subtraction, and when I say subtraction, the crust and trough are on top of each other. That's why the amplitude gets subtracted. That is what it means. Okay, now energy of this is lesser. We have seen this, right? That's why it's lower, and therefore it is more stable. This energy is greater than that of the atomic orbital. In fact, it is greater than this. That is why it is not stable. Okay, atomic orbital's energy is like this, bonding is lesser and this is greater. Alright, now electrons in this bonding molecular orbitals increase the force of attraction. So the electrons in bonding molecular orbital will increase the force of attraction between the atoms and contribute to the formation of molecule or a bond. Whereas electrons which are there in the antibonding will contribute to decrease the force of attraction and it will not contribute to the bond formation. What is the meaning of this? See, ultimately two atoms are coming, correct? And when two atoms are coming, their orbitals overlap and you are getting some shape which we will understand. Okay, let me say that you are getting two molecular orbitals, something like this I will tell you. This is your bonding molecular orbital. This is anti-bonding molecular orbital. There will be electrons here. Each orbital, it's the same thing, alright? Maximum 2 electrons. This electron will help you to bring the molecule, two atoms together and form a molecule. Whereas if there are electrons present in the anti-bonding molecular orbital, they will make sure, it is going apart. Alright? And this are represented by, just like you have sigma and pi bond, you have sigma and pi molecular orbitals. So we write it like this I will explain, and here you write it as star. The star asterisk here represents the anti-bonding. Alright? Yes. So what should be the condition overall for the formation of molecular orbitals? The atomic orbitals which are overlapping must have comparable energy, same symmetry or proper orientation and maximum extent of overlapping. Okay, now based on that we will talk about types of molecular orbitals, shapes of molecular orbitals and finally get into the molecular structure. Alright, so which I will cover up in the next video. Bye bye for now.